Okay, great. So I am happy to be here and present this seminar. I didn't know whether Dan would give much of an introduction, so I was going to do this. So this is the second talk in the seminar series, and I'm supposed to talk about perennial grasses. He did give you an introduction, so I've been at WVU for 35 years, 36 years, and he told you that. So one of my important areas that I've been doing research on is biomass, and it's been mostly in association with this idea of coming up with ideas for post-mining land uses after we reclaim these coal mines. And so one of the ones that we hit upon in the early 2000s was the use of bioenergy crops. Now, some of them are very specific for mine lands, and that's what I want to talk to you today about. It's really in three segments. There's this sort of long introduction, which introduces the whole idea of bioenergy. And then we'll talk about some of the crops that are available, and then I'll give you some specific information about what I've done in West Virginia. So all of you probably are aware of these changing energy conditions and sources that have been going on. So this is a graph showing the energy consumption from 1776 clear up with some projections up to 2050. And the graph really kind of ends at 2020, and then I had to kind of put this other part in it. But what you'll note from this is wood was the major energy source way over here for much of the early period. Coal came into itself in mid 1800s, and you can see the black line has come up and down and up, and has been a major energy source. And over the last 3 to 4 years, it has declined greatly. Here's petroleum, oil in the brown, light brown, and then of course natural gas is this blue color, which seems to continue to be going up. Prices have spiked a little bit on that, and so people are pretty disgusted with it right now, driving fertilizer prices and other things up. You'll note the nuclear has been here all along and seems to be sort of stabilized here. I wish it would come on a little better. And of course, here's the renewables, which is hasn't really grown much, but certainly from about 2000 on, and it will probably continue to grow as wind and solar get power. But one we'll talk about is liquid biofuels. And look at that. This projection from the EIA doesn't see that increasing, which is very disappointing. And I'll talk about why that might be the case. So let's talk about some of these others. So wind and solar, we know that those are making progress. And if you could choose any one of these particular energy sources, which one would you choose? I think most of us that have some knowledge would try to be switching to renewables, knowing that there certainly are some shortcomings, and they are not equal in availability, nor are they equal in price. And there are specific areas in the United States or the world where one or the other are certainly more available and cheap. So when it comes to biofuels, this is kind of an old slide, but it pointed out some of the reasons why we wanted to switch. And is it because of high energy prices? Well, not really. Our energy prices have stabilized or even declined, especially with this glut of natural gas. Are there concerns about petroleum supplies? Remember when we were fighting wars to make sure we'd have enough oil? Well, that's certainly not the problem. The US could supply its needs for oil, and they're continually finding new sources along with natural gases. So that's probably not the reason. But certainly, probably the reason that we are trying to make a switch to biofuels is this idea of environmental consequences and trying to move away from some of the fossil fuels. So biofuels do offer these ideas that carbon comes from photosynthesis, and then it goes through this cycle. There are less greenhouse gas emissions, especially the SOx and NOx that come from fossil fuels. Less dependence on foreign sources certainly supports rural economies, And there is this mandate from Congress that I'll talk about here in just a minute. So I'm going to focus much of my conversation on ethanol because that's one of the major sources of the use of bioenergy, even though we can burn it and we can do some other things with it, make some specialty products out of them that we'll hear about later in this seminar series. But corn has been the major source for biofuel ethanol. And as we look at some of the graphs here again, 95% of the ethanol comes from corn grain, which a lot of people have been very disappointed about. And it has led to this idea of a food versus fuel debate, where corn grain perhaps should go to feeding the world's population rather than being used to produce ethanol. And so this cartoon depicts this struggle between the big business executive and those in other countries that need this fuel. And so the solution that we came up with a long time ago, probably in the early 2000s when I started working in this, is we, instead of growing corn on prime agricultural land, we should be growing cellulosic crops, and we should be growing them on marginal lands, because these cellulosic crops can grow productively on those types of land. There also is this mandate. In 2007, the Bush administration and Congress passed an act requiring a certain amount of our transportation fuel come from ethanol. And here's a graph that's sort of depicting this idea of since 2007 or so, this has been growing. And the mandate said, and there was a later one passed in 2009 that said that by 2022, we were supposed to produce 36 billion gallons of ethanol that would replace about, or be about a fourth of our transportation fuel needs. The US uses about 150 billion gallons of transportation fuels. And so this 36 billion gallons kind of represents that. We've been piddling around down here around 13 to 15 billion gallons, but somehow we had to ramp up pretty fast to this, which, as you'll see, we have not done. So this whole idea of using cellulosic biomass to be our prime source. And so here's the graph that shows how much ethanol has been produced. And again, you can see from 2007 when Congress made that mandate, holy cow, we were growing like crazy. And then again, supply and demand and fuel prices and oil prices, all those things interfered with this idea of increasing ethanol. And so the peak ethanol was produced in 2018 at 16 billion gallons. And since that time, we've kind of declined. So in 2020, it was 13.8 billion gallons. So we're not even close to the 36 billion gallons that we were supposed to produce in 2022. So it's hard to know where this is going to go. But again, because energy prices from the other sources have not been a problem, ethanol may not be a readily available source. So you all probably know that when you buy gasoline from service stations, that 15% ethanol is what usually comes in the kind of gas that we use. If you don't have a flex fuel car, then you better not be using anything more than that. So if it has a little decal like that, then you can use some of these other kinds of ethanol products. So here's the regular one, good old oil gasoline, $2.59. Here's the E15, which most of us can use, and the price is a little cheaper. But as you increase the ethanol content, you can see that the price drops. But even though those are lower prices, you better not be putting them in your car unless you have a flex fuel car, because they'll really heat up your engine, burns hotter. All right, so there are some steps to making fuel from these cellulosic crops. And so again, the idea is you have to go make the cellulose into sugars, the sugars then through enzymes, and then the sugars then must be fermented by microbes. Very simplified idea of how cellulosic ethanol is made, and there'll be some other talks later in this series that talks about the specifics of these enzymatic processes that have to happen, and then the microbes. The other thing that's important for you to know that there are a lot of different types of fuels that can be produced from these cellulosic crops. Ethanol is by far the most mature technology, and many of those enzymes and microbes have been worked out. But as you go down the list here, all of these that are important sources of energy or other alternative uses, they're not as mature, and they're still working out, so to speak, the bugs, the microbiology, and the enzymes to get those to break down to be more efficient. There are about 200 ethanol plants in the United States, and they have a total production capacity of 16 billion gallons per year. So it's pretty hard to get to 36 billion gallons when you don't have the plants. There's some being built, and you can see the location. They're mostly out here where corn grain is produced. And here's the biodiesel plants, about 124 plants with a 2.5 billion gallon per year capacity. All right, so we just covered a lot of material, and this is supposed to be a class, so let's kind of recap here. So I discussed some reasons for switching to bioenergy for transportation fuels. There's this debate about food versus fuel, which we can overcome by using cellulosic crops and using marginal lands. I've given you some ideas about current usage and production capacity and how we do that. And then there's this mandate. So let's see if you can answer a couple of multiple choice questions just for the fun of it. So the use of biofuels as transportation fuels, and you're supposed to answer yes or no. And if we were in a class and I could see your faces, you could either tell me you're very confused or not, but it reduces NOx and SOx emissions. Well, yes, and generally, because you're not burning the fossil fuels, which have concentrations of those. It increases the demand of food crops for fuel. Yes, of course it does. Will the use of biofuels stimulate agricultural systems? Yes. It's mandated by Congress. Well, it is. And it will reduce CO2 emissions. That one's probably not so straightforward. You still have to so-called oxidize or burn this material, so it's giving off CO2. But remember, it's this cycle where you're taking recent CO2 out of the air, making these crops, and then burning them. So it's more of a recent cycle rather than burning CO2 from old fossil fuels. Use of corn grain for ethanol reduces the amount for food. True or false? Well, true. How much ethanol is mandated to be produced in 2022? Well, you all should know that that's number 3, 36 billion gallons. What offers the best ideas for future ethanol production? Using cellulosic crops instead of corn? Yep. Grow on marginal lands? Yes, sir. Grow on reclaimed mine lands? Well, that's what I think, and I've been doing. And try to help countries become fossil fuel independent, or at least use lower amounts. Well, that's true too. All right, so that finishes the first section. Now let's talk about the biomass feedstocks. And then the third part is about my experiences growing these. So we'll talk about each of these very quickly and concentrate on the energy crops down here. But first, here's the 3 big sugar crops, corn, sugar cane, and sugar beets. We also know that we can use residues as cellulose. But again, we're working down here towards switchgrass. So there's several numbers of these sorts of things. So let's just go through these quickly. So number one, and I call it 1A, is the sugar crop corn. It is the largest supplier. And I want you to keep track of this number, 600 gallons per acre. So 600 gallons per acre at a certain yield, and that's in Iowa where you can get 200 bushels per acre. It does contribute to the fuel versus food debate. But again, when you start considering all the fertilizer, the pesticides, the tractor use, the fuel needed, the harvesting, transporting, reseeding, it's an annual crop. There have been arguments that this net energy gain is really very small and even negative. And so corn may not be the best idea to use for fuel. Here's sugarcane. And again, it grows great big. This is what Brazil uses a lot down. So it grows down the deep south of the US, but other areas. And again, it produces about this 600 gallons per acre when you have a certain tonnage of this material. So sugarcane is a good alternative. Sugar beets. Now, most of you have no idea what a sugar beet is. I do, because I grew up in Oregon where sugar beets, we had a big sugar refinery factory in Nissa, Oregon. And our farm produced sugar beets that we took to the sugar plant, we called it. These things have a lot of sugar in them. They grow in the northern part of the US, but look at the gallons per acre. So this is one of the best sources for ethanol that's used. The problem is these things are miserable. I moved sprinkler pipe in these things. You're always twisting your ankle on them. They have, you have to cut off the tops and then they kind of stick out of the ground. You flip them out. And, but again, there's the real idea here is that it is one of the better ones in terms of the number of gallons per acre. Good old sugar beets. All right, so there's the big three: corn, sugarcane, and sugar beets. Now let's talk about residues for just a minute, and then we'll jump into the real ones. So the residues, of course, are the things that are left after the corn grain has been taken off, and that is a cellulosic material. It goes through the same process. The biggest problem with removing these materials, those would normally be reintroduced into the soil to add to its organic matter content. Because it holds nutrients, it can help supply and keep those soils fertile and healthy. So there is this concern, if we start removing all these waste materials, the residues will be depleting the soil organic matter content. So, but when you add that stover or the residue, so here's our 600 gallons per acre in Iowa with 200 bushels per acre of corn. When we add the stover, we get about another half of that. So you get a pretty good, close to 900 gallons per acre if you're in Iowa where you have some pretty high yields. If you don't have as high a yield, much like what we get here in West Virginia, that total gallonage is about half. So anyway, there are some disadvantages to using that ethanol. And we can do that with the residue from wheat or oats or barley, same thing, but it's all the same processes that we have this soil organic matter depletion. It'd be better if we could plow that in or leave it on the soil surface to protect the soil and add that organic matter to the soil. All right, so that was my little discussion on some of the residues. Now we're ready for the cellulosic crops. The first one I want to talk about is switchgrass. It's a warm season perennial grass that's native. It grows pretty well in marginal areas. It reproduces from seed and it doesn't require many inputs. So here's some characteristics of an ideal biomass energy crop: that it has a C4 warm season photosynthetic pathway. It's perennial. This is a really important one that I'll hit upon here in a minute, that it partitions the nutrients back to the roots upon senescence, and you can use existing farm. So switchgrass has been called this model bioenergy crop because of some of those ideal traits. So it has high yields without much input, don't have to use fertilizer and pesticides, and it's the C4 pathway. So here's this idea about translocation. So during the growth of switchgrass, as it's putting leaves and biomass on the surface, so it's taking up nutrients, minerals, fertilizer nutrients from the soil and making the biomass. But upon its death, or as it starts to senesce in the fall, one of the great things that happens with most C4 or many C4 crops is that those nutrients then will be translocated back down into the crown or into the roots where they're stored and used for next year's growth. Well, that is just great because this material is what we want. We want the carbohydrate material, not all these nutrients. Those nutrients are really contaminants. And so the best way to harvest this material is not to do it when it's green, but to do it after it senesces in October, November, December. And there are fields that are sometimes left till February, because then all the nutrients then have been translocated back into the roots. Great thing about switchgrass. Here's a quick graph on what kind of yields you can get from switchgrass on good sites. And here's this Schmer study that showed on marginal cropland they could get from 5 to 11. And so my goal has always been, if we can produce 5 metric tons per hectare or megagrams per hectare, we would be doing great. So that's switchgrass. The second one I want to talk about is Miscanthus, another one that I've got some experience with. It's also a warm season grass, that C4 photosynthetic pathway. It's a perennial grass. It's native to Asia. It is reproduced by rhizomes or stolons. So it's part of the root. And it, again, requires few inputs, but it has really high biomass. And so I'll give you some data about that. So again, here's all the ideal traits for Miscanthus. And the really other good thing about Miscanthus and really switchgrass is that the stand can stay there for 10 to 15 years without rejuvenating it, reseeding it, or having to go through it. So here's some growth that we had on a mine after only 2 years after planting those little sprigs. And after 6 or 8 years, this stuff continues to grow, and it's an incredible plant. Of course, there's a variety of forage equipment that you can use with switchgrass and with Miscanthus. Of course, you have to do it slower because there's so much biomass compared to our typical, 2 tons per acre C3 grasses. A third one that we are now just starting to do some work with is biomass sorghum. It's a warm season grass, but it's an annual. And this is what I'm worried about a little bit, because one of the ideal traits of a bioenergy crop is that it's perennial, so you don't have to reseed every year. So you have to seed annually. And I just don't know enough about it to see, there's some pictures of it, but this is one that we will be seeding this year, and we'll see how it does. Another one that I don't know much about is elephant grass or Napier grass, Uganda grass. Those are all sort of the same type of grass, a pennisetum, and they are warm season grasses that are perennial. They also reproduce through rhizomes, and that's how you have to plant them. Few inputs. So again, mostly grow in the southern areas that are more tropical. Now, next time, I think Sean Grishecki will talk about willow and hybrid poplar and maybe some other woody species, but that is, my task is perennial grasses. So there they are. There are some others that you can use. Kochia is kind of a weed out west. Hemp, of course, we know a little bit about, but grows very fast. Okay, so I've asked you to remember those gallons per ton. And so there's our switchgrass and Miscanthus based on a certain amount of tons per acre. And we've done a bunch of work on calculating theoretical ethanol yield. And those are pretty close to the numbers that we get. So it's pretty similar to corn, especially when you can add in the stover. All right, here's an ethanol plant in Windsor, Colorado, produces 40 million gallons. And so there are a number of these around. Okay, here's our next section. We just finished section 2. Let's talk about some questions. So from which crop does 90% of the ethanol in the US come from? Ta-da, all of you know that answer. Corn, number 1. What biomass bioenergy crop has been called the model crop? Well, I told you that, and that one's certainly number 4, switchgrass. I would go on to say that Miscanthus certainly rivals that because it has many of the same characteristics and traits. Which crop can give the greatest yield of ethanol per acre? Well, again, all of that's dependent upon productivity and how many tons you can get off. But remember, sugar beets was the one that had that pretty high number by itself. But we know that when you have high miscanthus or switchgrass, or if you have high corn and stover, you can get big numbers. But sugar beets was the one that kind of came out on top, close to, I think it was 800 gallons per acre. And which crop should we emphasize to use to meet the renewable fuel standard mandates? Well, certainly these latter ones, the cellulosic crop ones. Okay, so the third part of this, I want to just give you some ideas of actual studies that we have done and give you an idea of the kinds of yields that we've gotten on these marginal land, surface mine land. So we've got a whole bunch of sites all over the state where we've planted these. Some of them are new, some are quite old, like Hampshire and Hobet, and Colmac, we've had it there for 15 years. So that we're going to talk about these two first. Remember that Hampshire is a good site, and by that it has good topsoil, good soil fertility. Hobet, not so good. So here's the results after 7 years and 3 different varieties of switchgrass. And with the good site, we got 19 metric tons per hectare, 6 and 10. On the poor site where there's no soil, we got much, much lower yield. So here's some pictures. Here's the Hampshire, the good site after 2 years, really filled in great. And this is a reclaimed mine land. And after the 7th year, this stuff was, you couldn't even hardly walk through it. This cave-in rock was just crazy. Very impressed with that side. And these are 1 acre plots. We had replicates and have certainly published this information. Here's the Hobet site where we had no soil. It was mostly rock. It sort of developed gradually and very slowly, but for the most part, it was less than 2 megagrams per hectare, even after 7 years. And again, you can look that up on a site. We published this switchgrass yield on reclaimed surface mines a while back. Let me tell you about Alton. This is a wonderful site where we had 3 different plants, several different varieties in 1 acre plots replicated on a surface mine down in Upshur County. And for the miscanthus, we seeded the switchgrass like regular, and we used Canlo and Bowmaster varieties. For the miscanthus, we had 2 different types. One was kind of a public type, another one was a private type. We got this as sprigs. So they weren't actually rhizomes, but we had these little sprigs. And so we hired some tree planters to come in, and here's the sprigs in their bags. They walked along and punched a hole and jammed the sprigs in. Those little guys just grew like crazy. And after a year or 2, that was over your head. But you can also plant miscanthus with rhizomes. And we've had several of our students doing that. A fun day all around. And again, here's the miscanthus from the sprigs after 2 years at 15 metric tons or megagrams per hectare. And 5th year, a different variety, 13 metric tons. And after 7 years, this stuff just keeps growing and filling in where the sprigs were planted. And so here's some yield data. The private variety seemed to do a little bit better early on, but then sort of stabilized out with the public variety. And for Miscanthus, our goal has been 7.5 metric tons. And we've published all that information in bioenergy research and other places. And then the last site that I want to talk about is this one called the Wilds over in Ohio. This is where we were able to get a fairly big chunk of land and plant this. This is a unique site. It's where they have a little zoo there that you can go to. Anyway, it's just great. But in this case, we killed all the existing vegetation, and then we drilled into, no-till drilled into the material that had been killed. And after the first year, of course, you can see the switchgrass coming on pretty good. And after 5 years, again, we had really pretty good growth. The soil here was moderately good. And again, we got moderate to good growth, 8 metric tons per hectare. And the Miscanthus there also did exceptionally well, easily 15 metric tons per hectare on this old miserable reclaimed site, moderately good reclaimed site. Here at the Ohios, they harvested it and have been doing that for some time, and they've been using regular hay equipment, and those are the bales that they're collecting off these sites. So here's the switchgrass. All right, well, that about finishes it up. So I tried to answer these questions. Why do we need biofuels? Can we grow them? I hope I've convinced you that we can. But why haven't we moved from 12 or 14 billion gallons of ethanol to the mandate up to 36 billion gallons? Well, again, it's a lot, has a lot to do with the prices of oil and natural gas. So if I was to summarize this up, perennial grasses do show great promise as bioenergy crops for ethanol and for all these other uses that you'll be hearing about later in this seminar. I'm also part of a project where we're trying to co-fire using waste coal and bioenergy crops for a power plant that we're working on. And so that would be a nice connection, getting rid of the refuse or the waste coal and supplementing that with bioenergy crops. So there are other uses besides just ethanol. Switchgrass and Miscanthus have demonstrated high growth potential, certainly on marginal lands and on our reclaimed lands. And we are looking at trying to test some other grasses. And of course, there are other woody species that are being used. So let's do these last little questions. What offers the best ideas for future ethanol production? Well, I hope I've convinced you that using cellulosic crops is way better than using corn. And we can grow those on marginal lands rather than taking the prime farmland areas. And we certainly can grow these on reclaimed mine lands, especially those where good topsoil materials have been placed. So the fuel of the future is going to come from a lot of different things. Fruit, like that sumac on the road, or from apples, weeds, sawdust, almost anything. There's fuel in every bit of vegetable matter that can be fermented. Way to go, Henry Ford, 1925. Okay, Dan, that's where I'll end. I told you it'd take about 30 to 35 minutes. I think I was right, pretty close to that.
Excellent. Thanks so much, Professor Skousen. We have a few questions already. So as other people are typing their questions into the question pod, we can start with our first one. This one comes from Jared Morse, and he's asking about the first section of your presentation when you noted the projected growth of biofuels versus and said that we haven't really reached that mandated level. And he asks, could you attribute that lack of projected growth for biofuels to the mechanical issues and lack of energy BTUs per US gallon associated with biofuels? So I think he's asking about the end use issues of the biofuel as opposed to the feedstock and supply side.
Yeah, again, because there's less energy kind of per ton of material, coal has a certain BTUs per pound. And of course, it's like 12 or 13, 14,000, whereas these cellulosic crops are more like wood, around 5, 6, 7,000 BTUs per pound. So part of the issue is transportation, trying to get these materials somewhere where they could either be burned or where they could be fermented or go through another plant. The other part is just that this is still sort of a developing technology. We're pretty satisfied with coal and oil and natural gas. And when those prices have not gone up like we expected them to, thinking that biofuels and nuclear and some of these other things would replace them, it's just removed the need for us to move to them. And so those are the two things that just I didn't expect to happen.
Great. We have a question here from Richard Bergman asking about the productivity, these impressive productivity numbers you're showing us. He was asking, would you clarify this productivity? Is that a per year amount? And maybe you could just kind of clarify some of the different ways that productivity is sometimes displayed and how that can be confusing sometimes.
Yeah. So on our sites, when we were taking productivity, we would make sure and mash out all the previous year's growth. And so we were trying to measure annual growth. These weren't cut like in a large scale farming operation where, you know, cutters came in and removed every bit. And so we weren't removing all that biomass. And so the material was actually falling back down into the ground and sort of decaying there. So all of that would have some influence on how, in a real large scale situation and commercial scale, how that would all work together. And, you know, that's a good question. And whether these soils, especially these marginal land soils, would continue to support the nutrient requirement that these plants would need. We know they don't require near as much as some of the other crops, but they do have to have something in order to put that kind of biomass on. So, yeah, so that's probably what needs to be done next. And if that's what I had more of a chance to do, I would scale it up like we're trying to do with the wilds, cutting it off annually every year and then measuring that biomass so that we get a better idea of how those plants respond under that sort of system.
Great, thanks very much. We have a question from Sal Grover. Sal really likes Miscanthus, and he's asking, why is the Mass Bio project looking more at willow and switchgrass and not seemingly not so much at Miscanthus? He notes that there seems to be a lot more literature on Miscanthus on marginal lands than willow, for example. And it seems that Miscanthus maybe yields more than willow on marginal lands. Would you respond to that?
I probably shouldn't. I should allow Sean to talk about that and some of the other people that have been doing that research, even though I've been part of that with Jamie Schuler. There is a lot of work in the literature, and it's not just here. A lot of people are doing that work in Canada, and I've been trying to keep up with that, but willow has really great potential also. Again, he'll talk about that, but if you can do that in a pretty quick cycle of 3, 4, 5 years, and you're getting 4 to 5 year or 5-inch DBH material, it produces a lot of biomass, So anyway, Sean should be able to answer those questions. I'll try and make sure and ask Sean to address that. But Miscanthus is really an impressive plant, no doubt about it.
Now, Jeff, some people have some concerns about the invasiveness of some varieties of Miscanthus when grown. In your work, what precautions are taken to prevent or monitor for the potential spread of non-native plants and their, to try to make sure that we're not accidentally creating problems with invasiveness?
Nope, that was certainly one of my concerns early on. And thinking that somehow this stuff would just rhizome out and make these big clumps and just take over acres. That has not been the situation. And again, maybe the marginal lands have something to do with it that have caused it to sort of stay where it's put and hasn't had a chance to really move out. But I'm just really surprised. Part of it is that it doesn't seed. The seed is not viable, so it really can only spread through rhizomes. And with these sort of soil depletions, it just hasn't moved. So if we were to go to those sites now, even now that they've been there 16 or 18 years, you'll be very surprised that they're still sitting right in our 1 acre plots, that they just haven't grown outward of that. They've grown kind of in, the clumps get bigger, but they just don't spread and head over the hill.
Jenna Brickner has an interesting question for us. She's asking, well, about how much marginal land is available in the United States for biofuel production. How does that compare to the amount of biofuel that's needed in the United States? And she notes that there's also an issue of food scarcity being a growing concern, that insofar as available agricultural land may be reducing in terms of its availability also.
Okay, good questions. I'm not sure I'll get both of them, but let me try. Thanks for the question, Jenna. So there is a lot of reclaimed mine land in Appalachia, and even when you consider all that land, probably only maybe 20% of even that would be available that would have the right slopes and have all the other conditions that we could still farm it. I mean, you can't get much greater than a 15 or 20% slope, or you shouldn't. So there is a lesser amount than all the mined land. And we have about 200,000 acres in West Virginia. So even 20% of that would knock that down to, 30, 40, 50,000 acres. But again, whether we could get that done is another issue. I've been doing this for 15 years and I've talked to coal operators, and I've had a few of them grow it, of course, on some of these sites that you've seen, but it's not a traditional way to do that. I think the other question related to regular agricultural land and whether the concern that we're using those lands for something other than producing food. And I'm not sure if that was the right question, but yeah, well, I don't think that's what we probably should be doing with that good ag land. We should probably be doing the best, the most suitable, highest potential yield and crops for those good soils. Maybe Dan, you could tell me that second part of that question again.
Right, I think the concern was that maybe some of these abandoned lands would be better repurposed for food production if we're losing a lot of arable land already. Yeah,
good point. And that has been attempted, and that's certainly a lecture we'll have in our class on post-mining land use. But again, many of the lands are not suitable to row crops. And we have some here in the northern part of the state, southwestern Pennsylvania. But again, slopes and soil depth, soil fertility are all issues of whether we could get enough productivity from those soils to make it worthwhile.
We have a question from one of the students here in the classroom.
Oh, so I come from an area where a lot of farmers will sell their land because it doesn't produce well. And do you think that this produce well for food crops? So do you think this would be a solution for some preservation? I'm part of a farm preservation group. So do you think it'd be a solution to grow biofuel, like maybe switchgrass, because maybe they already have the hay implements for this? This would be a solution for them, because like you said, it has less inputs. It's kind of like you plant it and forget about it, and it is very beneficial to the area. So do you think it's a possibility for these farmers to implement so they don't have to sell their land and if you know, like there's less development and stuff like that?
Yeah, so it really depends on the end use, and that's what I've tried to emphasize all along to these landowners that have these properties. If you're going to grow some kind of agricultural crop, and switchgrass and miscanthus are ag crops, you have to harvest them every year, or you should if you have a place to take them. If there's a problem with that, if there's a lot of rocks on the surface, it's too steep, it's got other wet, dry problems, it's just not a good use of that land because of the effort it takes to get the productivity and the material off. My other area that I work a lot in is reforestation. And so many of these reclaimed lands should absolutely go back to what they were before. Now, there's not a lot of profit in it because you have to wait 30 or 40 or 50 years to turn a cycle of a forest harvesting practice. But those are really the better uses because they stabilize the land, they hold it together, they fit in well with the rest of the landscape. So if you're not willing to do this effort for an agricultural crop, whether it's a row crop or a crop that you have to harvest every year, or for grazing, you just have to recognize and decide what you want to do. Again, that's the other use of these lands, is just plant a C3 grass and legume, and you can either hay it if you can get on it, or you graze it, which is what much of the land is used for, because that's the easiest. Cows can walk around and
All right, terrific. I think we're at the close of our allotted time for today's seminar. So I just would like to thank you again, Professor Skousen, for your presentation and for the discussion. I think it was very interesting and stimulated a lot of thought here. Thank you very much to all the attendees for participating in this week's seminar, and we will look forward to seeing you hopefully again next Monday at 12:20 for our next Mass Bio webinar. Thank you very much.
All right. Thank you.
Okay. Thanks, everyone. Have fun? Was it good?
Yeah.
It's interesting. He covered a lot of topics, and there are a lot of nuances to some of these issues that are brought up. We could probably talk for hours about a lot of them.